Hi people, this is me answering the NEET 2021 Unit 3 and 4 exam. This is going to be a little bit faster than the TSSM one because we're probably going to visit quite a few of the concepts that TSSM covered in this exam as well. And if I've already done that in detail in the previous exam, I'm not going to waste your time by doing it twice in this one. We're just going to get through the answers, and I'm going to assume that you can that you have already learnt the detail that I need you to. However, if we find something new, absolutely, we're going to get into it with a fine-tooth comb. All right, this first recording is going to be, as per usual, the multiple choice questions only, and then I'm going to split the written part into two other as well, so there will be 3 different videos that cover this exam. All right, let's get into it. As usual, I'm expecting that you've got this with you. You've got the actual question book with you. You might even have the solutions in front of you as well while you're listening to this. That's fine. Some of the questions I'm going to show you because they have diagrams in them. Some of them I won't. I'll just read them out and I'll explain the answers. So question 1 is one of those ones that I'm going to draw a little diagram for. Let's do that right here. So question 1, there is a magnetic field with a north pole, a south pole, and there's another magnetic field caused by a current carrying wire. Now it says current, so it's right-hand rule, all right? It's positive current. Unless it says electron flow, you have to assume it's all positive stuff. All right, and there is a point between them, P. And the question says, which one of the following arrows best represents the direction of the magnetic field at point P? There's a magnetic field caused by this, and there's one caused by this. Okay, so the magnetic field lines right in front of a north pole will be going that way. Right? So, excuse me, lines of magnetic field from this source, the orange source, are going that way. From the pink source, from the pink source, you have to do this right-hand screw rule. Remember this one? Right? Your thumb points in the direction of the current, which in this case is out of the page, up towards the camera, and my fingers will point in the direction of magnetic field lines. So the magnetic field lines here are going down where P is. Right? So you have to resolve those two vectors. So if P is being pushed that way and pushed that way, it's going to go that way. So that is the answer you're looking for, and that's option B. So the answer to question 1 is B. All right, question 2. You either know the formula or you don't. It's just asking you to find the electric field strength of something. Charge has a magnitude of 10 microcoulombs. Which one of the following is closest to the magnitude of the electric field at a distance of 1 millimeter from the charge? All right, well, the formula that we're using is E equals KQ on R squared, right? Which is the electric field equivalent of gravity, the force due to gravity, being what is GM on R squared, right? Same sort of deal. Excuse me. The only trick with this one is that they've given you bad units. So they've given you microcoulombs, which you have to convert to coulombs for the charge, and they've given you millimeters, which you have to convert for meters for that. But apart from that, it's just put the figures in, get the answer, and the answer happens to be D, I think, for this one. Yes. Okay, here's question 3. Hopefully it's big enough for you to see. You've got it in front of you anyway, doesn't matter. All right, diagram shows the path of an electron. It's negative, left-hand rule, okay? Electron through a magnetic field B. Okay, the electron enters the field there, exits there, has a circular path inside the field. You know the deal. Right, the speed of the electron is changed to V on 2, and the strength of the magnetic field is changed to B on 2. At which point does the electron now exit? Okay, well, the relevant formula here is this one. R equals mv on BQ. Right. This is the formula to calculate the radius of that circle, right? It's from a combination of centripetal force, mv squared on R, and F equals is BQV, right? If mv squared on R equals BQV, you juggle that around, you end up getting this. Okay, so if the velocity is halved, right, if all of those numbers come to a value R, of R that is like that R, because that's the center of the circle that it's going around, and then we halve that number, and the strength of the magnetic field is halved as well. We halve that number and we halve that number. That fraction is going to stay the same, isn't it? Right? So if that's changed and that's changed by the same factor, the total that's going to come to is going to be the same. So in other words, the radius is going to be the same. So it's still going to come out at n. So the answer is C. Question 4 is a good one. It's an easy one to get wrong because some people are not going to read that slowly enough, right? Especially when they put something in bold, right? From each plate. This matters. Okay, it says point P is midway between two charged plates at a distance of 10 centimeters from each plate. So that's 10 and that's 10. So the distance between these plates is actually 20 centimeters, 0.2 meters. That's going to change the answer. All right. The plate potential values are V volts and 0 volts as shown. Okay, which one of the following correctly represents the potential and the magnitude of the electric field strength of point P? Okay, this is not an easy question. Before we go any further with this, these figures that doesn't mean 5 volts, that doesn't mean 10 volts. That means 5 times whatever V is. All right, we don't know how many volts V is, but it's 5 times that, 10 times that. That's what they mean. They're not actually meaning volts, right? Because the units of this isn't volts, it's actually volts per meter. All right, it's electric field strength. And the formula for the electric field strength is V divided by D. And the D here is 0.2 meters, right? So 0.2, so it's going to be whatever the voltage is divided by 0.2. And if you divide something by 0.2, that's the same as multiplying it by 5. So the answer for the electric field strength is 5. So it's got to be either A or D, okay? So now you come over here, and the potential at P should be half of what the potential would be there, all right? It's got all of the potential V here. Once it is let go of and it flies down that way, because of course it's a positive charge, a test charge is always positive, it's going to have 0 volts, so it's going to have exactly half as many there. So it's going to be V divided by 2. So the answer is D. Question 5, let me straighten this up. Another fairly visual question, so I've got the paper in front of you here. Okay, rectangular coil is rotated at a constant speed within a magnetic field. In other words, it's one of these little AC generating motors, right? Produced by 2 poles from 2 different magnets. Now that phrase, I just want to that confused a few people when this was given out, right? 2 poles from 2 different magnets, that just means this, right? This is not one magnet. That's one magnet over there, that's another magnet over there. That is 2 poles from 2 different magnets. That's all that phrase means. Every now and then that sort of confuses somebody. A graph of the EMF output from the coil versus time is shown below. Okay, so the peak is 5. Again, whenever you get a graph, whenever you get a diagram, just take 10 seconds and actually look at it. Just go, yeah, and move on. Just have a look. This is the EMF. It peaks at 5 volts, right? And this is time. All right, that's pretty much all we need to know. It doesn't go down, so it's been rectified. It's been turned into DC. And you know what turns something into DC? A split ring commutator. So, which of the following circuit configurations results in that output? All right. It's got to have to be A, because this one is not going to have any sort of magnetic field lines going in the right direction. There's a north there, there is a north there. They're almost going to cancel each other out. That won't do anything. That won't do anything either. This will give you AC because it's got a slip ring commutator, and this is going to give you DC, which is what the graph shows. So the answer is A. Question 6, the RMS value for the EMF output is, and this is where you had to have read the graph. A lot of people don't notice that 5 there, right? They just look at the graph and, well, it's DC, but where are all the numbers? That's where the number is. It's on the graph. They didn't tell you that anywhere in the writing. And they didn't tell you it in part 6. So you have to know that the peak value is 5, peak divided by root 2, 5 divided by the square root of 2. And again, for a lot of multiple choice questions where there's a calculation, quite often you don't actually have to get your calculator out, right? 5 divided by the square root of 2 is going to be less than 5, right? It doesn't matter what it is. You know it's going to be less than 5 because the square root of 2 is more than 1. 5 divided by something more than 1 is less than 5. So it can't be that, it can't be that, it can't be that. It's got to be that without even touching a calculator. The answer to 6 is A. Question 7, let me center it for you. There you go. Okay, 2 masses, M1 and M2, are connected by a light inextensible string. That just means it's not stretchy and we don't have to count the weight of the string in calculations, right? Hanging on a pulley as shown. All right. The mass of M2 is greater than the mass of M1 and M2 is accelerating downwards. As soon as something's accelerating, you know that the forces aren't balanced. So that force there is bigger than that one. Right? And it's winning the tug of war. It's accelerating downwards. M1 will be accelerating upwards. Okay, so the tension in the string is, okay, comparing it to M2G. Now M2G, that's just mg down here. That's the force on M2 that's pulling it down. Right? And the force on M2 that's pulling it up is the tension in the string. If they were equal, it wouldn't be accelerating. If the tension in the string was bigger, it would be accelerating upwards. This would be going down, right? But where this is accelerating downwards, it told us that, so that must be bigger than the tension. So the tension in the string is smaller than M2G. Let's have a look. Less than M2G. The answer should be C, and it is. Okay, done. Question 8, while I've got it on the page. A boy of mass 60 kilograms squats down, then jumps vertically upwards. He takes 0.5 seconds to jump from rest to 4 meters per second. All right, the magnitude of the impulse imparted by the boy, to the boy by the earth is what? Okay, two formulas for impulse. And it's actually the force times the time that the force is being applied, or it's the change in momentum. Right? This one, you've got the M, you've got the V, you may as well do change of momentum. While the kid was squatting, there was no momentum. After the kid had accelerated, excuse me, there was 60 kilograms times 4, mv is the formula for momentum, right? Delta mv. 60 times 4 is 240, so the change of momentum here is 240 kilogram meters per second or Newton seconds. So the answer has to be B. There you go. Question 9, you need a little bit of about year 8 maths to do this one. Graph below shows the gravitational force acting on a falling object versus its position from the center of the earth, okay? So 10 to the 6 meters, that 10 to the 6, that's millions. Millions of meters is thousands of kilometers. So 6,300 kilometers from the middle of the earth. Gravitational force is that. 7.16 kilometers from the middle of the earth. 7.16 thousand kilometers, sorry, from the middle of the earth. Gravitational forces calm down a little bit. Okay, so the work done by gravity to move an object from there to there is, okay, how do you do this? Work equals force times distance, right? That's force, that's distance. So that's area under the graph, okay? So you calculate the area basically of this trapezium. And this is why I said you need some grade 8 maths. You need to know what the formula for the area of a trapezium is, or you're doing the rectangle and then you're going to do the triangle. But either way, that's how you do it. Excuse me. And you also need to understand that because that's millions of meters and not meters, the answer that you get is going to be in gigajoules, not joules. That's millions of meters. That's thousands as well. Excuse me. You can leave it, you can convert your answer, get your answer in a different unit. All of these have different numbers, right? So when you get your answer, when you do all the calculating and you get 702 as the first 3 digits of your answer, it doesn't really matter where the decimal point is, right? The only one here that's got 70 and 2 on it is C. So again, you don't need to be particularly precious about getting the answer exactly right for a multiple choice question. They normally design it so that if you've got it right, you don't have to fish around too much looking at the other answers for possible. Question 10, Lorentz factor question. A traveling subatomic particle has a Lorentz factor of 1.2. How fast is it going? All right, so we're using Lorentz factor here, which is 1 over 1 minus v squared over c squared. Sorry, square root of. All right, now when you look at the solutions that they've given you for NEAP, they basically go straight from that to another formula. I'm just going to show you that that formula is derived from this one. Okay, so if you square that, let me just do it on the other page here. Let's do it properly here. Okay, so Lorentz factor is 1 over the square root of 1 minus v squared on c squared. Square both sides, Square both sides, therefore Lorentz squared equals 1 over 1 minus v squared on c squared. Okay, invert both of them. 1 minus v squared on c squared, equals 1 on Lorentz factor squared. Therefore, 1 minus the 1 on the Lorentz factor squared equals v squared on c squared. That is basically swapping those over. And that becomes negative, and that negative becomes positive. Right? Therefore, square root all of this now. V over c, which is the square root of v squared over c squared, equals the square root of all of that, 1 minus 1 over Lorentz factor squared. So that's what we're using. Right? The solutions that NEAT gave you just said, well, use this. They didn't tell you where it came from. That's where it comes from. All right. So basically you use that, you plug in 1.2 for the Lorentz factor, and you end up, and you put 1 there for speed of light, and you end up getting 0.55 for V. So that's the answer. And what option was that? Was it A, B, C, or D? That is B. So the answer to 10 was B.